Welcome to this video on computational physics. This video will be just a introductory video on computational physics, just to get us started in understanding how some elementary computational physics is done. Notice also that this video could easily also go under other titles. This video could be also called Euler's method, or numerical differentiation, or projectile motion, or fundamental theorem of calculus. These are all basically the same things, but we're going to use projectile motion here to just give a physical demonstration of what's going on within the mathematics. And basically here, hopefully in the next 10 or 15 minutes, you'll see that with some very simple definitions and some simple free software, we'll be able to basically replicate almost all of Calculus 1 and all of Physics 1 and be able to solve all those equations numerically that we get there. So before we get to the numerical part, let's look a little bit at the analytical part about what we'll be using to actually do the numerical part. So let's switch over here to the paper. Hopefully, yeah, good. So what are we going to do here? So for projectile motion, you guys are probably have seen something like this, right? If we have a constant acceleration, what's going to happen? Well, we're going to drop a ball. If we have constant acceleration like this is our acceleration. That means the velocity is just going to, and we'll draw this as time. Our velocity is just going to continually increase, all right? So if you step on the accelerator in your car and there was no wind resistance or anything else, your velocity would just go up and up and up, 10 miles an hour, 20 miles an hour, 30 miles an hour. So your velocity as a function of time would just go up, assuming that your acceleration stayed the same. Your position would start off moving slowly because, of course, you're moving slowly, right? And then it's gradually going to pick up, and then it's going to go like this. So x of t, right? So if acceleration equals a constant, then velocity equals that constant times time. This is a linear line. And the position equals, well, let's say v naught is 0, right? Equals 1/2 a t squared, right? This is quadratic, and this goes quadratically, right? If I flip this graph upside down, this would also be how a ball falls due to gravity, right? You're just going to accelerate more and more and more. All right. So you've probably seen this kind of equation, right? So x equals x naught plus v naught t plus 1/2 a t squared. This is a very well-known formula. When is this true? Notice that this is only true, right? This is the part that sometimes gets lost. This if with two f's means if and only if. If and only if a equals a constant, right? So this formula is true if and only if a equals a constant. If a is not a constant, then this formula is no longer true, right? So if we have wind resistance, for example, or any other kind of drag or friction or change in any other of the parameters, this is not going to be true, and we'd have to do the differential equations. So maybe a good example of how this starts to break down is, let's think about something like a rocket, all right? So if we have a rocket, we're going to have something, well, we'll need drag. So what's the force due to drag? Well, depending on the size, you'll have something like the force of drag equals some constant times the velocity, right? So it goes opposite the velocity, all right? We can also, this would be linear drag. You could also have something like v squared and the v hat. This would be quadratic drag, right, where it goes like the square. Things like rockets and cars, typically we want to think about v squared, the quadratic drag, all right? And so if we do this, then we're going to see that for a rocket, we're going to have the force is going to equal the mass times acceleration, which is just mass times x double dot, right? X double dot just means a second time derivative of position, which is acceleration. And this is going to equal minus c x dot, right? If we have linear drag, minus d x dot squared if we have quadratic drag, right? And we'll have other things, like we'll have the thrust pushing up, and we'll have, what else will we have? Minus mg here, right? Because we'll have gravity pulling down, right? You can already start to see this differential equation here is not so fun to solve. We could probably solve this differential equation under some constraints, and it'd be kind of an ugly equation, but we could probably get it done. But notice even this is a simplification. If we have a rocket that's shooting up in the air, right, the rocket is also going to be changing its mass, okay? So the mass is also a function of time. So we're going to have the mass equals, let's say m naught minus alpha t, right? This is just saying I'm burning, so alpha would be the burn rate. So I'm burning this amount of fuel, right? So now my mass on both sides is going to be dependent on time as well, right? And of course it gets even worse because we've made other assumptions, like gravity is a constant. Gravity is not necessarily a constant when you're a rocket because you're moving far enough away from the Earth that the gravitational force is actually changing. And if you remember, right, this just means G is no longer G anymore. The force of gravity equals, minus big G m1, m2 over r squared and the r hat. This is the generalized definition, where big G is the gravitational constant. And in this case, this would be equal to minus G, m of the rocket times mass of the Earth over x squared, right? And this is especially annoying, right? Because x squared is now a function of time, and mass 1 is the mass of the rocket, and the mass of the rocket is changing, right? So you see we're getting we start to get coupled differential equations when everything is changing here. This makes it incredibly difficult to solve to get an analytical solution, okay? So how are we actually going to go about this numerically? So to deal with this numerically, what we're going to do is basically use the fundamental theorem of calculus. So theorem of calculus. All right, so the fundamental theorem of calculus, well, we can draw a little plot. So generally speaking, let's say we have this curve, and we have x, and we have x plus delta x. All right, that means this point here, and we have this point here. This point is f of x plus delta x. This point here is f of x. All right, so what's the slope of this line? Well, the slope of this line, which we define as the derivative of f of x, equals f of x plus delta x minus f of x, right? That's this distance right here. In other words, that's the rise, all right? We need to divide that by the run, which is this distance right here. And this distance right here is x plus delta x minus x, which is just delta x, okay? So this is the definition of the derivative. Let me scoot that over so you can see it a little better. And of course, this is the limit as delta x goes to 0. All right. So we're going to use this definition of this fundamental theorem of calculus to great effect to be able to solve this equation. All right, let's get a second page in view here. All right, so what we're going to do is, so this is true as long as delta x is small, all right? So if delta x is small, this is, we may want to make it for small time steps. So let's go ahead and do this exact problem here of a dropping ball, right? A simple question we know the answer to already to see if our equation works, all right? So we'll want to set up something like a table where we have time on one side, and we'll have the position, we'll have the velocity, and we'll have the acceleration, okay? And this will be our plot. And again, we'll have our acceleration. Let's make our life easy and say acceleration is 10, right? Instead of 9.8, let's not carry all those decimals, all right? So if acceleration always equals 10. All right, and let's do it for time steps. Again, let's make our life easy of 1 second. 0, 1, 2, 3, 4, yeah. 5. All right. And again, let's make our life easy again and say we start at 0, 0 in position and time. All right. So what should this velocity be? What should the velocity after 1 second be? Well, we already know through the fundamental theorem of calculus that velocity right, is defined as the derivative of x, right, in this case, right? Or we can say, we also know acceleration equals the derivative of v. We're going to use these two facts, okay? So that means velocity defined as v dot defined as acceleration equals v of t plus delta t minus v of t all over delta t. Rearranging this equation, we have v of t plus delta t equals v of t plus delta t times a. All right, hopefully you see how I just use some algebra to rearrange that equation. So now, what is v of t equals 1? Well, v of t equals 1 equals v of 0 plus delta t times the acceleration. All right, so that just means 0 plus 1 times 10, so the velocity is 10. All right, let's try to make this, square this up a little bit so we can see what's going on. All right, so what's the next velocity? Well, the next velocity at v equals 2 equals the old velocity at v equals 1 plus acceleration times time. So it equals this number here plus the acceleration times time, so this is 20. And so we can see what's going to happen. This is going to be 20, 30, 40, 50. And this is just linearly increasing, so good. We have acceleration, we have velocity, we have time. Yep. So velocity behaves as it should. All right. What about position? Well, position is going to behave under the same rules. That is to say, we can just switch all the v's for x's. So x of t plus delta t is going to be x of t plus delta t times v. All right. So what's our next position? Well, it's going to be the previous position, so 0 plus the velocity times delta t. So this is going to be 0. Okay. What's our next position? Our next position is our old position, which is 0 still, plus the velocity times t, which is going to be 10. What's our next one? Our next one is going to be 10 plus the old one, which is 20. So this is going to be 30. And the next one is going to be 30 plus 30, which is going to be 60. And the next one is going to be 60 plus, is going to be 60 plus 40 is going to be 100, right? So I'm adding, how did I get 100? It's the old velocity, which is 60, plus delta t, which is 1, times this velocity, which is 40. So 60 plus 1 times 40 is 100, right? And I'm just doing that everywhere. 60 was 30 plus delta t times 30. That's how I got the 60. And the same thing is going on here for velocity. The velocity was just the old velocity plus the acceleration, right? The old velocity plus acceleration, right? So each new row in the chart is just affected by the rows above it, all right? So if I plot this, I'm going to get x equals 0, 0, 10, 30, 60, 100. You should recognize that this is going to be this. So this is x of t and v of t. And indeed, we get the behavior we think we should get. All right. You should notice that this is a little rough in this case, right? And what happened to the 1/2 at squared? Well, typically we're going to choose, and in the computer this is quite easy. By hand, I chose a big T, delta t, just so it was easy to see what's going on. But in computer, you're going to choose small delta t's. And you're going to choose small delta t's because you notice that I didn't have the 1/2 at squared term here. Okay? I didn't have that, and I don't need it as long as delta t, right, squared is much, much smaller than delta t. All right? As long as this condition is true, then I don't need this 1/2 a delta t squared term because it will be negligible, right? So we want to go to smaller and smaller delta t's until that's true in our computations. And we probably won't get to it today, but later on we'll use what's called RK4. This is fourth order Runge Runge-Kutta. This is fourth order Runge-Kutta. This is an even better approximation to Euler's method to give us more numerical accuracy with easier computation. So we'll go into that later. But for now, let us move this over to the computer, over to Excel for a second. And then, let's see, right-hand screen, perfect. Little technical difficulty there. All right, I think we're back. Good. Okay, so let's go ahead and execute this in Excel. All right, in Excel, so I like to keep my variables over here, and I'll just make these variables, I'll just put these in yellow, and these will be things that I can change. So let's just say delta t equals 0.1, and let's go ahead and make our columns of time, position, velocity, and acceleration. All right. So let's say we have x, let's say we need to know x0 and v0. So let's again start at 0 and 0 to make our lives easier. Let's start time at 0 as well. So our time column is just going to increment every time by delta t. So this column just equals the previous column plus delta t, right? I need to do one more thing, and that is in Excel, you use the $ to make sure that it doesn't move down when you copy it. So this next cell is going to be the previous cell plus this number, not this number, right? So we want to make sure it doesn't move down, and you do that using the $. And then we can just copy a bunch of those columns. x0 is just going to be x0, v0 is just going to be equal to v0. Let's set a equal to whatever number we put here. So let's make this 10. Let's just call this acceleration and make it a constant. All right. So now that we have this, we can implement our algorithm. And this, again, we'll want this to be a $. We can copy that down. All right. What's our velocity? Our new velocity equals our old velocity, right? Equals the cell above it plus delta t. And again, I'm going to put $signs here because delta t is not going to change. It's whatever this number is for all the cells times, times the acceleration. All right. So this is our velocity as a function of time. And you see that it just increases linearly in this case, right? As we expect that it should. So what about our position? Well, our position is basically the same idea. I could even just copy this over, but I'll show you how to do it. So our position equals our old position plus delta t. This is again a $sign times the old velocity. All right. So let's go ahead and look at some of these. Let's look at t versus x. And to do that, we go insert chart and this guy. So we see we have this trajectory going on. We can also have t versus v. And we have this linear increase as a function of time. All right. So it is behaving how we expect it to behave. Let's go ahead and make this look maybe like something more interesting. Let's make it look like a ball that we threw up. So in that case, acceleration equals minus, and let's go ahead, we can put 9.8 instead of 10 here, minus 9.8. So now the ball is falling down, but let's give it an initial velocity going up of 10 meters a second, and there we go. Now we're, right, exactly what we did before, but you see, hopefully you can see my mouse here in this, in this plot here. In this plot, the bottom axis is time. So this is, let's move velocity. So this is time, and this is the position. So the ball is going up, 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 and then down, down, down in this parabolic thing that you're normally used to. All right. So we got the answer we were looking for, and let's go ahead and make this. And of course, the nice thing is here, you can just copy and paste, right? Page down, and then I can make this smaller. And let's delete this, and let's do this one more time. Insert plot, scatter. There we go. Okay. Yeah. So there's our trajectory. And now the dots are so close together you can't even really see the dots. Okay? If we wanted to, we could compare this to our formula in this case. Remember that this our formula that we derive for constant acceleration is x naught plus v naught t. So this is going to be v naught. So this is going to be this. So this is going to be v naught. Whoops. V naught times t plus 1/2 times a times t. And I can do that as well. And now if I'm lucky, so this is the let's say theory, right? So if we do x and t and theory and insert and this, yeah. The problem is they're so close together that you can't even see them apart. Hopefully you can barely see that on this. There you go. You can see that they start to diverge just a little bit here on the outer edge, right? So that is how good this calculation is to tell us this exact trajectory, right? And I can change whatever I want to here, right? So I can change this to 12, right? And it changes the trajectory. I just threw it up harder in that case, okay? So why is there this slight deviation? Well, this slight deviation just comes from delta t not being infinitely small, right? And you saw how easy it was. I could just copy and paste and make this delta t twice as small and do it over, and I'll get better and better approximations. And like I say, in the future, we'll use other tricks, the fourth order Runge-Kutta especially, to solve this differential equation. And we'll use adaptive step size and other tricks here to make sure that this is correct. But, okay, so we have this trajectory. But we already knew the answer, right? We already had the theory, so why did I go through all this rigmarole to make sure that we were able to do it numerically? Well, it's nice to be able to do it numerically because, of course, now I can add in things that I couldn't deal with before. Let's say we have that. Force of drag, right? So let's have a coefficient, right? So this is a coefficient. Let's call this the coefficient of linear drag, and let's call this the coefficient of quadratic drag, right? So I'll make this 0.01 to start with. So let's say we have quadratic drag, all right? We'll also need the mass. Let's just make the mass equal to 1. Okay, so let's say we do something like drop a ball out of an airplane. All right, so x is 0, x0, 0, v0, 0, a is minus 9.8, right? And the mass is 1. All right, so what's the acceleration going to be? The acceleration is going to still be minus 9.8, but as it goes down, right, it's going to be minus the velocity times, well, let's say minus the velocity times the absolute value, the absolute value of the velocity, right? This is just v squared, and I'm doing this so I keep the direction. I want it to be in the opposite direction of the velocity. So this gives me the direction, right? And this gives me the v squared, and then I'm going to multiply it by v quadratic. And let's do $sign. And you can see when I start that this is just minus 9.8. But if I copy this down, right, I can even look at this. You can see that acceleration gets less and less and less. Well, why? Because gravitation is pulling me down at 9.8. But as I speed up and go faster and faster, the wind resistance is actually pushing me back up, right? So that means it gets less and less and less, all right? And that's what we expect. Let's go ahead and look at the position with respect to time. Oh, I guess we have it. We already have it right here. So we have the position with respect to time, and let's turn this up a little bit. So what do we have going on here? Well, we have the theoretical, and in this case we shouldn't really call it the theoretical. We should call this without drag, right? So without drag, this line is just going down and doing our standard thing as if we drop something. But with drag, you notice that we start along the same trajectory, but then we go in a straight line like this. And if we look at time versus velocity, we'll get an idea why this is. It's not what I wanted. Time versus velocity. Good. So our velocity starts at 0, right? And then we're getting more and more negative velocity as we're falling out of the plane, going faster and faster and faster. But as we're going faster and faster and faster, that means we have more and more drag. And so around minus, in this case, minus 30 meters a second, around minus 30 meters a second, my velocity doesn't increase anymore. Why? This is what's called your terminal velocity. This is when the wind resistance is equal to the gravitational force. And so this is actually what we expect, right? So that the velocity is going to be flat, and of course the derivative of the velocity is the position. So when the velocity becomes constant, that means in this plot, you're just going to have a straight line. So this is going to go flat, this is going to go straight. So we're easily able in this case to deal with something like wind resistance, where before we would have to think about what this is like with a quadratic equation, right? With a coupled differential equation, right? And it was pretty simple to do here. And of course, we can add everything that we had before in this equation. Let's see. We can add things like, I could add the linear drag. That's no problem. That would just be minus da-da-da, right? Well, minus the velocity times the linear drag coefficient. Right, so now I have linear drag and quadratic drag, right? So, and I can also have things like adding the mass, right? So it's no problem here to also do the rocket problem, and I encourage you to do this for yourself. You can also have the mass as a function of time, right? So I could have m0 equals 100, let's say, and this would equal 100, right? And then this would equal the previous one minus, let's say, alpha times delta t, right? So alpha, let's say, loses a kilogram a second, right? So in that case, the mass would also be changing as a function of time, and then you'd use this mass to determine the acceleration, right? You'd no longer have 9.8, right? This 9.8 would depend on the mass you're using, all right? I assumed a mass of 1 to start, but right, this mass would be changing. So you just reference it, and the beauty is, once you've written this line of equations, you're done. All you have to do is just copy it down and plot it, because each line depends on the line above it in exactly the same way. All right, so maybe we'll do one more example here, just to show how you could do this with two dimensions, for example. So we can do the same thing, right? So, and of course, recognize that I made this rocket problem even easier than it actually is, because it's not only x, y, and velocity, position, acceleration, right? There's 3 dimensions of this as well. So let's go ahead and do time, x, vx, ax, y, vy, ay. All right. We'll do the same kind of thing. Define the time step 0.01. Whoops. Let's also define x0, x0, y0, v0x, v0y, theta, and v0. So in this case, let's think about throwing a baseball, right, at a certain angle. All right. So if we throw a baseball, we'll start at x0 and y0. Let's say I throw it at 10 meters a second at an angle of 45 degrees. that means the velocity in the x equals, let's see, cosine of theta. And of course, this is in degrees, so I'll make it into radians. So times pi divided by 180. Right, and the same thing, this is going to equal the sine of this times pi divided by 180. Whoops, of course, times V0 times V0. Good. So now our time will start at 0, and time is just equal to the previous line plus delta t. And we can just drag a few of those down. Our initial position, x, is going to equal our initial position. Our initial velocity in x is going to be this. Our initial position is y, it's going to be y. Our initial velocity in y is going to be y. All right, now let's think about our acceleration in x and y. All right, so it's probably good to have a mass here. So let's say our mass is 1. That's a pretty heavy baseball, but it'll make our calculation simpler. And let's add a column here just so I don't mess up and choose the wrong thing. All right, so our acceleration in y. Let's just start out with our simple guy. So the force in y is just, well, let's just say g is minus 9.8. So acceleration in y equals g, and again I need dollar signs, 9.8 times the mass, right? So this is the force divided by the mass. This seems kind of foolish, but we'll see why I need the mass in a second. So this is the acceleration, right? It's just minus 9.8. The acceleration in x just equals 0 in this case. Okay. This is just going to be copied down. This is just going to be copied down. All right. And now we can deal with the velocity and the acceleration. The velocity in y just equals the previous velocity in y plus the acceleration times delta t. Okay. Again, the new velocity equals the old velocity times the acceleration times delta t. All right. The new position equals the old position plus the velocity times delta t. Now, one of the nice things is if I do this, if I did this right, hopefully I can just, whoops. I can just copy this down. Good. So now we have these guys, and let's do this, and let's copy. And good. And now if I plot x versus y, insert chart with x versus y, something is not quite right. It doesn't look parabolic. Oh, this was just, there we go. So for some reason it wanted to act a little strange there. But now we have our nice parabolic arc. And let's go ahead and play with the axes here real quick to make sure that this is 15 and make sure this is, let's make this all right. I'm just doing that so that the axis doesn't change when I play with things. So let's have this here. And so now I should be able to do things like change the angle. So let's change it to 30 degrees. Yeah, so it got nice and flat. Let's change it to 60 degrees. It got, right, it went much higher, right? We can change it to 45. We can also change our velocity to 12. right? And it goes further, right? So we can re-enter any of these things and basically calculate this. So any kind of trajectory, this is perfectly fine. All right. So now that we have the basics, let's finish up with one more thing and add wind resistance. All right. So let's say see drag. All right. To do the drag, let's go ahead and make another column for simplicity, which is going to be the speed, and this is the square root. Whoops. The square root of Vx squared plus Vy squared. All right. So this is the speed, and so we have a new column that's called the speed. And to get the quadratic drag, we'll talk about this more when we talk about the drag, but the quadratic drag, right, needs to be in that direction. So it's going to be v squared, so it's going to be minus v, it's going to be minus the speed times the velocity. Okay, so that's going to be the quadratic drag. Oh, and of course, this is a huge number because I didn't add the coefficient of drag here. Times. So this is k, which is the speed, times the velocity. Yeah, let's go ahead and use that. And 0.01, let's say. All right, we can copy that down. And let's do the same thing here. This is going to be 0 minus the speed times, what happened here? Something strange happened. Oh, I didn't use the previous step, of course. So this shouldn't be, let's go ahead and move this. So let's reset this real quick. Okay, so of course you want to use the one before it. So this is going to be, yeah, you want to use the cells above it, right? You have to be a little bit careful in Excel. You don't want cells, right, depending on one another, right? So you always want the cell below to depend on the cells above. And now, good, all right. And now the acceleration equals 0 minus the speed times the velocity times the coefficient of drag. All right, and let's turn this back to 0. Yeah, so if I turn this to 0, this is just the old equation. All right, and let's turn this back to 11. All right, so you can see when I throw this ball, I'm throwing the ball with a velocity of 11 meters per second at 45 degrees, and this ball takes this trajectory and lands out here around whatever, 12.5. What happens if I turn up the wind resistance? Right, now it doesn't land at 12.5, it lands at 11.5, right? And if I turn up the wind resistance even more, now it lands at 8.5, and even more, right? So in this case, you can think about trying to throw something like a volleyball, right? Or not a volleyball, a beach ball. If you try to throw something like a beach ball, right, the wind resistance is going to fight you very hard, and the beach ball is going to start to go out, but then the wind resistance and is just going to lose all its oomph in that direction and then just kind of drift straight down. All right, so we can play with these parameters, right? And so throwing a volleyball really, really hard, right, goes out, but still the wind resistance is going to overcome it. Okay. So with wind resistance, now you can even think about playing with something like, what angle should I throw it at? So I can find the angle here. Is it actually better? So right now it's at just past 9.5. If I throw it at 45 degrees, what about 50 degrees? Well, it got less. What about 40 degrees? Right? That got more, right? So we can think about things like finding the range and going from there. All right? So you see how it's quite easy to add in things that would be incredibly difficult to do in differential equations, but numerically it's very simple. Once you have your spreadsheet set up, really it looks like you're doing a lot, but all you're doing is one line of coding, right? And each subsequent line is exactly that same line repeated over and over and over again. And all we've done here is use a fundamental theorem of calculus, all right? And so for a rocket, you could add another 3 columns for the x components. You could add another column that's the mass, right? And you could get very, very accurate, even using Excel, to find these kind of trajectories with time-dependent masses, time-dependent coefficients of drag, time-dependent gravity, velocity-dependent forces, all kinds of things going on there. All right? So I hope this was useful, and I hope you can see now that how easy these problems are to solve numerically, right? Hopefully this is fun and interesting, but realize there's also a place for the analytical solutions, right? These solutions give you an answer, but the analytical solutions are nice when possible because they tell you the behavior, right? If I ask you how this trajectory depends on mass or drag or theta, right? All I could do is just plug in new numbers and find the data, right? Whereas if I did it analytically, then I'd have an expression and I could say, oh, it depends on the square root of theta or theta to the third power or whatever the analytical solution might be, right? So the numerical is great when you want a quick solution, but it might not be the best way if you want the most meaningful solution, right? But now that you have this technique, even if you get the analytical solution, you should just double check, just save the spreadsheet, put the relevant parameters in, and you can always check numerically to see if your analytical solution is correct. All right, that's all I have for this time, and we will see you next time.